Hello and welcome. We are doing our seventh topic. We are covering recursion today. So we have a couple of learning goals. I have two different videos on recursion so that I can sort of show um, more complicated examples. So this is going to cover most of the basic stuff, and then I have another video that's going to be a little bit more complicated. So our learning objectives right now are creating and implementing recursive solutions to simple problems like mathematical calculations and traversing arrays, array lists, things like that. Writing recursive solutions to problems using helper functions and not using helper functions, as well as being able to actually identify and explain the base case and recursive step for different algorithms. So first thing we have to do, though, is we actually have to talk about how we would explain recursion to a 6-year-old. And this is a joke. We would explain it to somebody who's 1 year younger than ourselves and tell them to explain it to a person 1 year younger than them. And this will just continue until the 7-year-old explains it to a 6-year-old, and now we've solved it. So this is recursion, this idea of making our problem smaller and smaller and smaller until we hit the solution we're looking for. Here's a couple of funny memes about recursion as well. So the first one on the left, I know my left from my right. On the left, we can see somebody who's saying problems with recursion, and it's kind of like one of those ads you would like see on a tree trunk or something, or like at a grocery store, and they take a little tab where like the information on getting help is, but on the little tab it says problems with recursion, please take one. And this sort of just continues. And then the last one here is learning to program, make a recursive function. And if you don't have an exit condition to stop the problem from getting smaller and smaller, as you can see, this meme is inside itself, which is inside itself and continues. Okay. Lastly, I asked ChatGPT to explain recursion to me in a funny way, and this is what it came up with. It said, imagine you're trying to clean a messy room, and you start by picking up a book and opening it, only to find a smaller, messier room inside. So in order to finish cleaning up your room, you step into the room in the book to clean it up. And while inside, you find another book with an even smaller, messier room. And this just keeps going with you finding smaller and messier rooms within rooms. Each time you're thinking, this time I'm definitely going to be able to finish cleaning. But just like in recursion, you need to actually find a room that doesn't have a book with a room inside of it. We have to find that smallest step. Otherwise, we're going to be cleaning rooms forever, cleaning rooms within rooms. Okay, so recursion is when we take a big problem and we solve it by solving smaller subsets of the problem first. This is actually surprisingly easy when we're talking about implementing it in code. It's just a method that calls itself. So let's look at a traditional example. Now, this problem isn't necessarily what we would call naturally recursive, but we can do it anyway. So let's think about what's called a factorial computation. When you have some value n and you want to compute the factorial value of it, you take 1 times 2 times 3 times 4 times 5 all the way up to times n minus 2 times n minus 1 times n. So consider for a second 3 factorial. You would do 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 6 times 4 is 24. And 5 factorial is 1 times 2 times 3 times 4 times 5, which I think is 125, but I can't remember for sure. But this is a loop, right? This is an iterative loop where we start at 1 and then we go all the way up to and including n, and we just multiply them over and over again. We start our n factorial off at 1 for n, and then for our I equals 2, because we've already done 1, and we can do I less than or equal to n, and we just multiply it in. 0 factorial actually is 1 as well, as a little tidbit. And then you return the value. This is an iterative solution because we iterate through the numbers using a for loop, right? So this is called an iterative solution. Now, if we wanted to do this recursively, we can sort of figure out what the pattern is that we saw happen and write it recursively. So we know that 0 factorial, as I just said, is 1, and 1 factorial is 1, and 2 factorial is 2, and 3 factorial is 6, and so on and so forth. What we can see is that When n is less than or equal to 1, it has to be 1. There is no negative factorials. So if n is 0 or if n is 1, the answer is 1. And for all other values of n, we need to multiply n by everything that comes before it, right? N has to be multiplied by n minus 1, n minus 2, n minus 3, all the way until we hit 1 or 0. So we can code it like this. We can have an if statement that tells us that if n is less than or equal to 1, we know that that means that we need to say that the value is 1. So we return 1. And in all other situations, we take our current value and multiply it by the value that comes before us. So factorial n minus 1. So yeah, we can make any loop recursively. And I have a really fun little way of doing this. I'm going to go ahead and share my screen here and I'll show it to you. Okay. Oops. I know how to share things. Hold on. Advanced? No. Apps? No. Maybe? Looking to figure out how to, oh, there it is. Via cable. There we go. So you should be able to see this. Yeah. Okay. Good job, me. So let's take our for loop for a second that we used for factorial. We had, oh my God, I have to make sure I can actually see what I'm doing here. Okay. We had some value int factorial n that started off as 1. And it's important it starts off as 1 because if it starts off as 0, 0 times anything will just be 0. So we started off at 1 very, very purposefully. Also because in our base case, n equals 0 or n equals 1, we wanted to return 1. So this starts off at 2. This went until we were at n. We went up one element at a time, or one value at a time. We took our factorial value, we multiplied it into I, and then at the bottom, we returned our factorial value. Okay, and this was all inside a method. I'm going to move this over so I have room here. This was all inside a public static int factorial method. Sorry, writing public static every single time is just so exhausting. So I'm just doing PS to make it shorter for public static. Okay, so now let's look at the factorial or the recursive solution. Public static int factorial, that stays the same in this situation. And then we said if our n value is less than or equal to 1, we knew that we were going to just straight up return 1. Otherwise, we had to say return n times factorial n minus 1. And that was our whole product, our whole process. Okay, so these were the two things we saw, and it was kind of confusing to look at because it's really hard to see how we go from one to the other. So what I'm going to do is I'm going to alter my iterative solution just a teeny, teeny, tiny bit. I'm going to go ahead and start my my n value off as the first number I'm going to multiply in. So rather than this starting at 2, this is going to go n, and this is going to go I greater than 1, I minus minus. So it does the exact same thing, only now instead of going 2, 3, 4, 5, 6, 7, 8, 9, whatever, n, we're going to say n minus 1, n minus 2, n minus 3, all the way down until we hit 2. So that's all I've done is I've negated it. It's going to make this a lot easier to see what's going on. Now, this didn't change. Those two are the same for both our iterative solution, iterative, and our recursive solution. Let's just take a look here. Now, notice this variable was getting returned before, right? That's our return. Our return is going to be the same. Think about the scenario where n in this solution over here equals 1. When n equals 1, our for loop doesn't run, and we return n. And when n equals 0, our for loop doesn't run and we return n. When n over here equals 1, our for loop, nothing happens. We just return 1, just like our iterative. And when n equals 0, we also will return 1, exactly the same. So those two things are true in both solutions. Okay. Now let's do some more highlighting here. When we start off at n and we check if n is greater than or equal to 1, we're asking ourselves, are we going into this if statement or this else statement? So when we go into, actually, we can highlight this also in pink. Because basically, if we don't go into our for loop, if we don't have to iterate again, that's because our if statement was true. Our inner for loop is actually our else. So more specifically, this right here. That's else. Because if we didn't go into the if our n is not less than or equal to 1, it must be strictly greater than 1. So that's our else. This right here is us taking our current total and multiplying it by whatever I is. And I is n, and then n minus 1, n minus 2, etc. That's this right here. That's what that is. We're saying n times whatever comes back from our recursive call. This I minus minus is this, n minus 1. Because if you think about it, our for loop is doing exactly that. It's doing I minus minus starting at n. So first it's n, then it's n minus 1, n minus 2, n minus 3. Same thing that we're doing here. And then this idea of going back up in our for loop is exactly what this factorial call is. It's just going back to the top of the for loop with I minus minus. Only in this case, it says n minus 1. Had we renamed I to n, these would look n to I, these would look exactly the same. Okay, let's go back to sharing our desktop here. Hold on. It's crazy to do this. I hope all this worked. Who knows? I'll have to do a check to see. Okay. So when we want to break our problems like these down, as we saw, we had if and else. We had two different cases. So we had our base case and we had our recursive case. Now our base case is the simple or smallest subset of the problem. So in our factorial code, we said, what's the tiniest thing that you can make a factorial of? Well, 0 factorial is 1 and 1 factorial is 1. Those are both the same, effectively, right? 1 factorial is just doing 1 times 0 factorial. 2 factorial is doing 2 times 1 times 0 factorial, right? And 0 factorial is 1. So that's our base case. That's our smallest case. And then our recursive case is calling our own method, so calling ourselves, and doing this stepwise decline into the problem space. So going from 5 to 4 to 3 to 2 to 1 to 0 until we hit our smallest subset of the problem. So our base case is a way to stop the method calls. While we're writing this code, it's really important we have some way to stop our method calls. We can't make calls forever. If we do, it's a little bit like an infinite loop. Our code won't stop, except it will, because reasons. There are more explosions when you go forever with no base case, and I'll show that code in just a moment. So infinite loops don't cause any additional memory usage because loops are happening in the same method call. We just keep doing the loop. But recursive calls are kind of like making new pancakes on our runtime stack. If you remember from a few weeks ago, I always talk about runtime stacks like pancakes, like a pancake stack. And every method call is a new pancake. And if you keep making method calls, eventually our stack is going to get too tall and it's going to fall over. Let's look at this in some code. Stack Overflow example. Stack Overflow example.java. Let's go over here to our desktop. Okay. And we'll make our main. Now imagine for a second if my stupid floating meaning bar is in the way. If I wanted to try iterative infinity. Okay, we're going to make this method. I won't be able to run both of these methods because this is going to be iterative infinity. Oops. Public static void iterative infinity. Whoa. Don't know what just happened. Doesn't matter. Everything's fine. Okay, so what would iterative infinity look like? This. Let's just make a variable. Int I is equal to 0, while true, I plus plus, and then when we're done, we'll just print out I. But of course, what we can see here is that if we say while true with no way of making the loop false, our loop is never going to stop running. So let's just run this code just to prove a very obvious point here. Unreachable statement. Oh my God, it even knew that that was unreachable because this is while true. Okay, let's take this one step further. If I is less than 0, break. Now I will never be less than 0 because I'm starting it at 0 and I'm only ever incrementing. But now at least I'll be able to compile my code because Java by default is not smart enough to realize this will never happen. Stack Overflow. My code just keeps running and running and running until eventually my I variable overflowed. Like my I variable got too big. I could do this in even smarter, like, I don't know if it's smarter, but an even better way where it's truly infinite, where I can say like I minus minus right here. So if I is less than 0, we break out, otherwise make I go down and then make I go up. So I will actually never change in this silly method. And now my I doesn't actually ever overflow. I just spin forever. I'm stuck right now. I'm completely stuck in here. And I can show it even further by moving this print line statement right in here and printing out I each time to figure out, hey, what's going on? And I just never, my code never stops. I'm going to get zeros all the way down. If you can see in the bottom left corner, you'll see that like my scroll bar is just like slowly, continuously going down forever. So if I command C to stop it, like this literally just never stopped. It just kept running and running and oops, where did my mouse go? This always happens. There we go. Running and running and running forever. Now this is what happens when we have an infinity loop. Okay. Now, what happens when we have recursive infinity? Well, again, when we called iterative infinity, we made one pancake on our stack called iterative infinity, and it's kind of just like we kept eating it forever. We never finished eating it. We just got stuck here eating it forever. So our code didn't explode because it was still a manageable amount of pancakes. It was just one pancake, but we never finished eating it. So it just kept going forever. Now, here's the difference. When we look at recursive infinity, let's like pass in a variable here. Let's pass in the variable public static, whoops, void recursive infinity. We'll take an n and we'll write it the same. So if n is less than 0, break out of our code. Break. You can even say break here. That's fine. Here we can say else, call recursive infinity. And before we were doing n++. So there we go. And once again, if I run this code, what we will see happen is I will eventually, I don't know what I'll hit first. I don't know if I'll hit my integer getting too big or if I'll hit a stack overflow. I actually have no idea, so we can try it. I'm not going to actually do ++. I'm going to do +1. Order of operation issue might appear otherwise. So here, every time we call recursive infinity, it's like making a new pancake. And if I keep making new pancakes, eventually my entire stack of pancakes is going to topple over. So eventually what ends up happening is we end up with what's called a stack overflow error. Oh, you don't like it there. Okay, we'll just do this is really bad programming practice, but we'll just say return empty. Something else we could do, I hate leaving empty if statements, is we could negate our if statement like this. And just say, if n is greater than or equal to 0, because that's the negation of less than 0, do the recursive thing. And that's okay too. So watch what happens when we run this code. Whoa! So we didn't actually do everything forever. In fact, if I tried to print out n, which I will do, we'll see exactly at what point it explodes. Oops, I forgot to recompile. We should see exactly at what point it explodes. There we go. we can see exactly at what point explodes. So we can see that we were very happily ever increasing our value. And before we even hit the int overflow value, well before actually, only at 43,825, did we hit our stack overflow error. So we managed to make 43,825 pancakes before our code was like, you can't keep making pancakes forever. And then it just exploded. Now, a lot of this is happening inside the Java program, so a lot of this doesn't really help us. But right here is where we can see the overflow happening in our own code, line 22. And that's because we kept, pardon me, line 22 isn't actually quite right. It happened on line 24. There it is. That's the one that kept getting called over and over and over and over and over again until finally our pancake stack, our runtime stack was full. We tried to add this print line pancake to the stack and our whole stack toppled over, right? We ran out of room, stack overflow. So our code overflowed. There we go. I'm very happy with the GIF that I found. Okay, so a quick reminder about stacks like we just saw though. This is how our programs run. Each method call can be thought of a little bit like a pancake on a pancake stack. And if we make a method call inside of another method call, just like when we call system.out.println inside of our main, it's just kind of like adding a pancake onto the stack before we finish eating the first one. So before we finish executing main, the println pancake, the println activation record gets added to our stack. Now, each pancake is chocked full of the ingredients it needs to make it yummy. So every method record on that runtime stack has all the variable information that it needs to run that one time. And then when a method finishes running, we can eat that pancake, we remove that activation record, and it disappears. However, our plates and our program can only hold so much before it topples over. You don't really have to keep this visualization in your head of what your runtime stack is looking like and all the variables that are in it and the returns and the calls and the line numbers. That's okay. We literally can just think about it a bit like pancakes and a little bit of magic that keeps things running. So too many pancakes get made without enough getting eaten fast enough, our whole thing is going to topple over. We can't finish eating our pancakes. Eventually, we run out of room on our plate. So the main takeaways here when it comes to recursion is that we need to find a way to solve our problem by using a solution that's slightly smaller than the version that we started with. It's the same problem, we're just solving a smaller case. So when we think about our refactoring problem, we start off with not refactoring, our factorial problem. We start off with trying to find 5 factorial, and in order to find 5 factorial, we have to take 5 and multiply it by 4 factorial. And in order to find 4 factorial, we have to multiply 4 by 3 factorial. And to find 3 factorial, we have to take 3 and multiply it by 2 factorial. And then to find 2 factorial, we have to take 2 and multiply it by 1 factorial. And to find 1 factorial, well, we just automatically know that 1 factorial is 1. So we can just say it's 1. And then we can now take 2 times 1 and we'll get 2. And we can pass that up. And we'll have 3 times 2 now, which is 6. And then 4 times 6 is 24. And then 5 times 24 is 125. And we now have our 5 factorial equaling 125. Now, sometimes it can be really helpful to write out a lot of like the formulas to solving the problem that you're trying to solve, looking for a pattern, because it's not always super obvious the way that just taking 1 off of n each time is. As long as you can prove that your solution works for a base case and that your solution works for 1 case up, it's probably going to work a lot. It's going to work for all your cases. And if you are really mathy, this is effectively a proof by induction. If it works for a base case and it works for an inductive case, it's going to keep working. So let's think about this a little bit. This is an aside, but it's another example. Teaching a cat to climb down a ladder. So imagine I want to teach my cat to climb down a ladder and the ladder has n steps. So we're going to make this really easy by using recursion. If I can teach my cat to climb from the very bottom step of my ladder to the floor, that's great. That's my base case. Then I know my cat's on the floor. And I can probably do this by putting a treat on the floor and putting my cat on that final ladder rung. And my cat is very motivated. She's going to jump down, eat that treat, and I did it. My cat can go from the bottom rung, the bottom stair, however you want to think about it, to the ground. Now, the recursive case is to consider that a cat can probably climb down k steps of my ladder. It can go from rung to rung. So now I just need to teach my cat to go climb down from one step to the next. I don't have to start from scratch. I can put my cat one step up. So now my cat's on the second last rung. I put the treat on the second rung, or the bottom rung, pardon me, and my cat steps down and eats it. And my cat already now knows how to go from the bottom rung to the ground because they did it last time in my base case. So now my cat can climb from the base stair or the base rung to the floor, and from the second rung to the first rung, and then from the first rung to the floor. Now, because those are the only two scenarios, either rung to rung or rung to floor, I don't need to keep showing every single sort of iteration. I don't have to show from the third to the second, second to third, first, first to floor, fourth rung to third, third to second. I don't have to do that every single time because I know that my cat has the knowledge from climbing down the second rung to the first rung to be able to do it again. So there's some magic in there that happens where I can say, well, if I know my cat can go from rung to rung, and I know my cat can go from rung to floor, there's no reason why my cat can't start at the top and make it all the way down to the bottom successfully. And that's exactly what we're doing here. I know that this aside might be kind of a confusing example for some people, but when I learned recursion, this is how it was taught to me. And I actually was like, wow, that makes so much sense. So I thought I would throw in this aside for anybody who's still struggling to sort of see how we can sort of just trust the process of recursion. So now the question is, oh, I gotta play this video, obviously. Why are we doing this if we can just use loops, right? If I showed you how to go from loops to recursion, recursion to loops, there's no real reason for recursion based off of our current amount of knowledge that we couldn't just solve it with a loop. And we're going to see in a second why we need recursion. So some problems are really difficult to solve iteratively and have really beautiful, quick, elegant recursive solutions. Now, that being said, just because we now know about recursion, it doesn't mean that we need to use it everywhere. It's just a really good tool for us to have in our toolbox. Because sometimes recursive might seem like physically shorter code, but it won't actually be shorter when we run it. And I'm going to show an example of that. So it's definitely worth thinking about. Just because this is like a hammer that we have in our toolbox, it doesn't mean that every single problem is a nail. We can't necessarily solve every single problem with recursion, even if the code looks super elegant to do so. Okay, thanks for that great video. All right, let's look at another scenario here. Consider the following method header. Let's write a method that takes in an array of integers and calculates the sum and returns that sum. Let's start by writing it iteratively, and we actually are going to write it out. Here it is, but I'm actually going to go ahead and write that code. Let's make a new class here. Array summation. That doesn't spell summation. Array summation. I can type. Oh my gosh. .java. Okay. So what do we call it? Sum of. Oh, and we probably need to make some kind of integer array data. And it'll be 1, 2, 3, 4, 5, 6, 7. It doesn't have to be in order. It doesn't matter what the data is. I'm just making my life easy here. We said it was going to return the sum of everything in data, and then we can go ahead and just print that up here. Now we need to make that method public static int sum of, and it will take in our integer array of data. Now this should be pretty straightforward for us. We're basically going to go through every single element in this list. I was going to use a for each loop, but this will look nicer if we do it this way, at least when we translate our code. We're probably going to need a variable that starts off at 0. And then we can just keep adding to this variable. So instead of factorial, where we were doing like a factorial of a given number, here we're just going to do a running sum of each element inside that array. And then we can go ahead and return that total value. And this code should work so beautifully. We're just going to give it a shot, make sure that I didn't make any crazy mistakes. Perfect. I don't know if that's true, but I'm guessing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is 28. Now I want to make sure because I am skeptical. 15 21, 28. Yep, it's 28. Great. Okay. Awesome. So this is how we do this with a for loop. And now we're going to write this code with a recursive solution. So public static int, we're just going to call it sum of recursion with an R there so that we can do this. Now let's remember that when we did the solution for the factorial, each time we ran our code, we decremented, we took one away from n. That's not really an option here. If data what? How exactly could we write this code so that when the user, whoever's in main, calls sum of on data, we're actually able to run this just like a loop, just like we did before? Here we had access to I, here we don't. Well, what we're going to do is we're going to write what's called a helper method or a bootstrap method. Let's just look at the notes first here, right? We can see that if our data.length is 0, we can return 0. That makes perfect sense. However, if our array is not empty, we need to take the current element that we're at, and how are we going to sum that first n minus 1 elements, right? We have no way of specifying how many elements there are left to sum, because we have to first take the sum of the first one, and then the first and second, the first, second, and third. And if we want to think about it by making the problem space smaller, it's like we want to take the sum of the very last element plus all the previous elements. And then the sum of the second last element plus all the previous elements. But how do we specify that? We're going to make an interface helper method. This is going to be an interface so that the user doesn't have to change what they send in, and they don't have to worry about if we're using recursion or if we're using a loop or whatever. And we're going to call a very secret, note the private right here, recursive version of our function. So the helper method allows main to stay exactly as it was with our iterative solution, but now we can use a recursive solution internally. And this is really important because it means if for some reason we are in a code base where a friend made an iterative solution and we know that it could be done a lot better with a recursive solution or vice versa, the main doesn't have to change. We only have to change our implementation of the logic. So over here, this doesn't change. We still call sum of data. Only now inside here, rather than calculating the sum directly, we're going to call our sum of r method on data and pass in our n that we want to start at. Now notice that this sum of r should only really be callable from inside this method. This doesn't really quite do that in this scenario, but if this was in a different like if this was in its own object or something, we would be able to say the main class can call this, but not this, right? We can use that private to mean that only other methods within the class, within the object class, has access to it. So now we actually can change this and make it n. And we can say if n is equal, if n is equal to 0, pardon me, we know that we need to just return 0. But in all other cases, we need to return our data at n plus whatever the sum of all the previous values are. So we call recursively data on n minus 1. And now to make sure that this works, of course, we want to make sure that when we compile this, we get the exact same answers before. Oh no, we didn't. I wonder why we didn't. So when we look at this, it would have been great if I would have kept the code that I had previously, but that's okay. We have to think about what this actually means, because I actually know why this didn't work, because we have to think about what n actually is representing, because n isn't representing in the way that I've written this the number of elements left. It's actually representing the index that we're looking at. If I wanted to represent this as the number of elements left, we'd have to pass in how many elements there are to start. That's not what I did. I passed in the index. Now, if I turn this into an index, hopefully we will recognize quite quickly that this if statement no longer makes sense, because index 0 is a real thing. It's the first element. So in this scenario, we don't want to return 0. We want to return whatever's in that spot. Okay, so hopefully that makes sense. But we're also going to see why this solution doesn't actually necessarily work in just a second. So we're going to run this and we'll notice that now we get 28 and that works. But that works for this data set. What happens in this data set, an empty array? Well, I can tell you what happens, and it's that we're going to be not working correctly because index of -1 doesn't work. And where does that happen? Well, when data comes in, it's going to come in here and it's empty. Our data.length is 0. 0 minus 1 gives us -1. Index comes in as -1. If our index is equal to 0, it does this. It's not equal to 0. It's -1. So then we come in here and we end up saying data at spot -1. So this solution doesn't work like this. Now we have a few options. Option number 1 is to say if our index is less than 0, whoops, if our index is less than 0, we can return 0. If our index is equal to 0, we can do this. Otherwise, we can do this. And in fact, with this solution, we can even just do this, and it will work exactly correctly as well. Nope, why not? If our index is less than 0, oh yeah, that is right. So that works now, and it doesn't have array index out of bounds. And if we put our original array back, we're going to get 28, and this works beautifully. But the name that I gave this variable is just so important here, right? Because it wasn't actually n representing n elements. It was representing the index. If I wanted this to rather actually represent n, now I could say if n is 0, I can return 0. But now this should always be referencing n minus 1 here, because then we're saying there's one fewer element to actually look at. So now when I run this code, we'll see that those changes allow for the same result. And if our data array is empty, this will also allow for a 0 result with no array index out of bounds. So naming that variable here made a huge difference in my own comprehension of what the point of it was, right? It made a difference to know if what was coming in was the number of elements or if what was coming in was the index that I should be including in my num sum, in my sum. Okay. So we saw that interface, and then we could see that we had a private method that should just be used internally and not by the quote unquote user or the main method, whatever. It should only be called by that helper method. That's the only method that should call this recursive version. You'll also notice in this example that the name of the method, pardon me, is actually the same. It doesn't have that R for recursive like I did. And this is actually a little bit more standard. And that's because this sum of here has a single parameter. This sum of has 2 parameters. And what that allows us to do is do what's called method overloading. And we can have the same method name with the same return type, both being static, but the difference in the number of elements here is enough for Java to know the difference. So when we say sum of here, this one knows it's going to call this one. So we're overloading the method name by changing other parts of that method signature to allow us to use the same method name more than once. And this is a bit more standard because it allows us to really easily see that this private method is associated with this public-facing method. So that is just a little bit more standard to do. So now we're going to write some code here. We're going to write some code to convert to write a method that will convert binary code. So we're going to pass in a number in base 10, so like normal human counting, and we're going to convert it to a binary representation of the number. Those are words. Okay. And we're going to return this value as an array of zeros and ones. And we're going to do it without a helper method. And we can do it without a helper method because we're going to have an array that's coming in and passing values around, or an array list, pardon me, passing values around. I wrote array, but this should say array list, and I'll fix that right now before we keep going so that when I upload this later, it looks correct. Sorry about that. And now we're going to have an array list of integers of zeros and ones that will represent the number converted to binary. So let's consider our two different cases here. Our first case is our base case where n is equal to 0. And if n is equal to 0, meaning that the value that got passed in is 0, we can just return an empty array list, and that's totally fine. Let's start by coding that up, actually. I like that idea before I just keep talking about it. Public class binary convert.java. Whoops. And then here we're going to do our main, and we call convert to binary. My floating bar got in the way again because that looks like words. Convert to binary, and we can pass in any number. We're going to start with passing in 0 because we just said that this should be binary representation. We're going to pass in 0 because we know that 0 should come back when this happens. Since we're using array lists, we're going to need to import java.util.arraylist. We're going to make this method public static. It's not void. We know that. It returns an array. Oops, that says arithmetic exception. Array list of integers, and it takes in the base 10 n value. And we just figured out that our base case should be if n is equal to 0, we're just going to return an empty array list. So we'll make a new array list integer, but there's just nothing in it. And that works totally fine. So that hits our base case. And now we said we're specifically doing this without using any helper methods. So let's head back over to our notes and take a look at what our recursive case is supposed to look like. Did I write array list properly? Okay, I did. Sorry. So our recursive case is for the situation where n is greater than 0. Now, if you don't know anything about binary numbers, that is going to be a big problem to solve this problem. But it's basically numbers represented with just zeros or ones, and their placement in the sequence of zeros or ones helps us sum up and determine their base 10 value. Now, there's a really simple recursive way to solve this problem. We take our value that gets passed in, our n value, and we divide it by 2. Now, if n is even, we're going to add a 0 to our array list. And if n is odd, we're going to add a 1 to our array list. Now, hopefully you're saying, wait a second, n mod 2, when n is even, n mod 2 is 0. And when n is odd, n mod 2 is 1. So this is actually really simple code. Oops, wrong way. So all we need to do here is, I remember how to do this. Make our array list. Wait. Return this array list. I want to make sure I'm remembering how to do this properly. It's pretty simple. To make sure I'm adding to it properly. Is there actually return? Hold on, I wrote this code and now I want to make sure that I do it properly the very, very first time that I show it to you. Because if I don't do it properly, I will just confuse all of you even more than I mean to. Okay. So we have to remember what this method returns, and this method returns an array. So every time we call this method, we want to call it, on base 10 n minus 1. We want to go down by 1 each time. And then what we're going to do is we're going to add to our array right here. We're going to add base, 10 n mod 2. So it'll be either 0 or 1, depending on if it's even or odd. And then we can return our array. Now this looks a little bit different than the previous one because the previous one we had our recursive call in our return statement. And this one's just a little bit different because what this is going to actually return is going to be an array, and we're going to add to it and return that. So think for a second, in the case where n is equal to 0, we're just going to have an empty array. Now when n is equal to 1, we want to return an array with the value 1 in it. So what actually happens is we make an array list here, because n will not be 0, it will be 1. Oh, I can't call it n over there because it's going to be base 10n. It's going to be 1. We're going to call convert binary 1 minus 1, which is going to return 0. right? So this is going to be 0. So we call it again on 0. When we call it on 0, this runs. And so now we make that empty array list, and that gets stored right here. And when that gets stored, the array list gets the value added to it, base 10n, which is 1 at this level, mod 2, which is going to give us just 1. And then we return that array. Now, in order to actually run this code to, pardon me, show it working, I probably need a print line up here. That says 0. That makes sense because this was 0. And if it's 1, I have to ooh, 1 array.add base 10. I'm not running the right file. That makes this a lot harder if you don't run the right file. Okay. Binary convert.java. Didn't name it properly. There we go. That makes way more sense for me, right? Like for me to try and run it and it be because I just don't know how to spell things, that checks out. There we go. So now we have an array list with the value 1 in it. If we put the number, like let's say 15, 15 in base 10 is 111, I think. Is that right? And sorry, in base 2, 1 1 1 1. I can see how good my base values are here. We end up with that is super not correct. And that's because this had to pass in the divided by 2, not -1. Good job, Lauren. Yeah, there we go. 1 1 1 1. It was doing too many of them otherwise. We're having our problem space each time. It is binary after all. Cool. Let's do 3. 3 should just be 1 1. Just picking some numbers that I happen to actually know so that I can test to make sure this works. That worked. That's fantastic. And 2 should be 1 0. We should test that more than just the 1 work. Perfect. Oh my gosh. Okay, so this one's a little bit more like crazy for our brains to think about. Let's look at why just one more time here, because it is super tricky for our brains to think about. Hold on. I know how to share things. I know it doesn't seem like it, but I do. There we go. That one's for binary search for later. Okay, so let's look at what actually was happening there, because this one is pretty crazy to consider. When we tried to call our binary search or our binary conversion on 2 in base 10, which should be 1 0, what's actually happening here is that we're making our problem space smaller, 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 smaller until the very, very bottom. And then we start to build up our solution, which is different than what we did with the factorials. Because with the factorials, what we did was we were doing the math as we were building down. We could think about it that way a little bit easier. But in this case, we can't. In this case, we take 2. Here's my runtime stack, and we say binary convert of 2. And before we do any work, we end up calling binary convert of 1. And before we do any work, we end up calling binary convert of 0. And on this one, we made our empty array list, right? We made an empty array list here, and that got passed back. And then when that got passed back, so this pancake got eaten and that got passed back, we added onto the array list that got passed back a 1. And then that got passed back. And this pancake got eaten. And then on this one, we added onto the array list 2 mod 2, which was 0. So we added a 0 onto this. And then that got passed back to main. And so we actually builded it? Wow, Lauren. We actually built our array list from the bottom up, as opposed to when we were looking at our summation, and it was a lot easier to see how we were taking 5 and then 4 and then 3 and then 2 and then 1, and we would just add each one together. 6, 10, 15, and so on. It was a lot easier to see it moving in that scenario where we had the return in the same line as the recursion, whereas in this scenario, we don't. It's a little bit trickier to see what's going on. Okay, let's just flip back to my code over here. Okay. So I have a bunch of pretty standard questions here that we typically do for great practice with recursion. So the first here is summing natural numbers. So doing a summation where we start counting, if n is 5, we would do 1, 2, 3, 4, 5 and adding them up. Very, very similar to factorials. We have reversing a string. So writing a recursive method that allows us to peel each letter off and build the string back up backwards. That reverse a string is very, very similar to converting to binary in the way that the string gets built. We wait until we get to the bottom with an empty string and then build it back up rather than like moving the characters around as we do our calls. Counting the number of digits in a number is a really great one. So for example, if their number is 12,345, the output should be 5. Note that we're not just turning the integer into a string and calling .length. That is not recursive. You need to leave the value as an integer to actually get practice with recursion. And then the last one here is the power of a number. So writing a recursive method that will take in a base b and an exponent e, and then it calculates b to the power of e. So if we took in 2 and 4, you would do 2 times 2 times 2 times 2. So you do it 4 times, and you get 16. So that's a really good one too. I would say number 1 and number 4 are the simplest to solve. Number 2 is a really great one for practice and doing string manipulation with recursion. And then question number 3 is probably one of the trickier ones, just because it involves you remembering how to do integer manipulation. When you're asked to solve something recursively on a test, if you use loops, you get a 0. If you are asked to use recursion to solve something on an assignment and you use loops, you will get a 0. So please make sure you take some time to practice this. My second video is also still on recursion, and it's just going to show some more advanced problems and some places where recursion looks great, but isn't actually that useful. So make sure you have a really solid foundation of practicing with these practice problems before you move on to the next video.